Now we are going to go over the concept of solution. By definition, a solution is a homogeneous mixture made of two or more substances. We actually have terminology to describe those two substances. To make a solution, you need a solvent and you need a solute at a minimum. The solvent is going to be the substance present in a solution in the largest amount, and the solute is going to be the substance in the solution that it is present in less amount. In order to make a solution, you need at least one solvent and one solute. But understand that in general, you can have solutions made by one solvent and many solutes. When it comes to solutions, understand that solutes and solvents may be in all states of matter. So that means that we can find them as solids, liquids, or gases. In table 6.3, we have various states for solutions. And we can observe that solutions can also be found in different states of matter. We can have liquid solutions, solid solutions, and even gas solutions. Looking through the examples, we can observe that salt water is an example of a liquid solution in which our solvent is water and our solute is going to be the ionic compound sodium chloride. An example of a solid solution is going to be an alloy. And alloys are going to be when we have specifically metal elements that are combined, but these combined elements do not make a compound. They are just going to be physically mixed and sitting next to one another, but there's no chemical bond between them. So, for example, gold alloy is the combination of gold and copper. Lastly, an example of a gas solution is going to be air. Air is mostly nitrogen because that is its solvent. Its solute, in terms of amount, the largest is oxygen, but air actually has different solutes, including carbon dioxide gas, water vapor, helium, just to name a few. On figure 6.12, we have an example of an alloy. There we can see stainless steel, which is an important alloy that it is utilized in surgical implants and instruments. I already established that when it comes to a solution, that is also known as a homogeneous mixture. Earlier in the semester, we learned how mixtures can be homogeneous or heterogeneous. In order to prepare a homogeneous mixture, the substances, meaning the solute and solvent, need to be soluble into one another. Soluble is a term that it is utilized when a substance dissolves in a significant extent in a solvent. We can see on letter A where we have a drink mix that it is placed in water, and we see a homogeneous mixture because the drink mix it looks uniform once it's placed in the water. If molecules or substances are not going to be soluble in one another, they make heterogeneous mixtures. And when it comes to this, we know that heterogeneous mixtures, for the most part, are going to be made by insoluble substances. An insoluble substance is going to be those substances that do not dissolve. In other words, they are immiscible and they do not combine. So we can see the different parts of the substance within the mixture. So in letter B, we see the heterogeneous mixture of oil and water. In this example, we can observe how oil and water do not mix. And then in our heterogeneous mixture, we have the oil and we have the water. We can observe all the different parts of our mixture. In order to make a solution, we have a term in chemistry that it is called like dissolves like. If the polarities of your solute and the solvent do not match, that means that the solute and solvent will not dissolve. That is because the forces between the solute particles are going to be too strong to overcome the interactions of the solvent particles. That's why when we're trying to make a solution, a good rule of thumb is that like dissolves like, meaning if you have a polar solvent, then you will be able to solubilize in it polar solutes or ionic solutes. On the other hand, if you have a nonpolar solvent, then you will be able to dissolve in it a nonpolar solute. So, like dissolves like refers to the likeness, meaning the similarity in polarity that are going to be shared between solutes and solvents. And as long as they match, they will be able to dissolve in one another. In figure 6.19, we can see an image of specifically an otter. And this is just illustrating how they're going to be swimming in water. But overall, what the image is trying to illustrate is that if there are environmental changes that affect the water, so for example, if there's an oil spill, since oil and water have different polarities, the oil will float and make a heterogeneous mixture with that water, and that can actually affect the wildlife. Overall, when it comes to homogeneous and heterogeneous mixtures, they can be classified as either true solutions, colloids, and suspensions. Let's actually define them so we can understand how these different types of mixtures can be classified. First, a solution is a homogeneous mixture of two or more substances in which the solute completely dissolves in the solvent, forming a single phase. When it comes to solutions, their particle size is going to be less than 1 nanometer. Their appearance is going to be uniform. And then when it comes to scattering light, if you shine light through it, then that's what the Tyndall effect refers to. There's not going to be scattering of light in a solution. Solution also tend not to settle because since they have a uniform consistency, we will not even be able to filtrate it. So we have an example of a true solution in the first image in the two figures that we have, the one that is on the left. A colloid, interestingly, it is a heterogeneous mixture, but to the naked eye, it actually appears as a homogeneous unit. The particle size of a colloid is going to be larger than the one in a solution. They tend to have particle sizes from 1 to 1,000 nanometers. Interestingly, colloids appear to be cloudy, but again, to the naked eye, they look uniform. If we try to look at to see how light is scattered in a colloid, there is scattering of light. That means that there is a Tyndall effect when it comes to the colloid. The particles in a colloid do not settle, and we need to utilize actually a special methods in order to filtrate them. Lastly, mixtures can be classified as suspensions. And a suspension is a heterogeneous mixture with visible particles that are dispersed within a fluid. A suspension is going to have the largest out of the three particle sizes in mixtures. The particle size is specifically larger than 1,000 nanometers. Most suspensions appear to be cloudy and they separate. In terms of the scattering light through it, sometimes they have a Tyndall effect, sometimes they do not. Suspensions will be the only type of mixture that actually settles. That means that you're going to see a separation and it's going to set in the bottom. And when it comes to filtration, you can actually separate the components of a suspension via filtration. As I was just mentioning, physical separation techniques can be utilized to separate mixtures of basically solutions, colloids, or suspensions because of their particle size. Let's actually talk about different physical separation methods as we can see it illustrated on the right side of the slides. The first one is settling. Let's establish that settling means that overall there's going to be particles that are going to found in the bottom of the container. In the illustration that we have specifically on the right side of the slide, we have orange circles representing a solution, green triangles representing a colloid, and red squares representing a suspension. We can see overall that when it comes to settling, suspension particles can settle on the bottom of a container due to gravity. This is going to demonstrate that suspensions are unstable and they can separate over time. Solutions and colloids do not tend to settle. Next, if we use a filtration method in order to separate a mixture, understand that overall, via filtration, we can observe that when this substance, that could be a solution, a colloid, or a suspension, is passed through a filter, solutions and colloid particles pass through the filtration system, and they're going to be found in the other end of the container. So that means that the filter paper does not hold specifically solutions or colloid particles. On the other hand, suspension particles can be separated by standard filtrations. And even though a colloid is a heterogeneous mixture, filtration does not separate it. Lastly, we have a semi-permeable membrane. Only solution particles are going to be small enough to pass through the membrane of a system. So if we have a membrane, which is going to basically contain either solutions, colloids, or suspensions, membranes specifically will retain inside of the bag, as you see in the last illustration, colloids and suspension, because their molecule size are larger, then understand that they're going to be retained inside of the bags, and only the particles that are part of the solution will actually come outside of the bag. We are going to specifically see how this plays a role in dialysis when we discuss it later in the semester, or actually later in this chapter.